Okay, another phenomena of sound that's actually fairly easy to analyze is what's known as beats. We hear beats. If you're a guitar player, keep referring to guitars, but you're trying to tune it, you might tune one to another string. You're actually listening, unless you got perfect tone or something, you're listening for the beats to go away. And when they do, the frequencies of two strings are the same. Well, anyway, let's take a little bit of a look at this. So we have a sound wave. You know, it radiates out in three-dimensional space, interfering with another sound wave. It radiates out in three-dimensional space. You produce constructive and destructive interference patterns as exemplified by the ripple tanks that we looked at and the pulses along a spring. But the sound waves also interfere in time. Okay, so as we look out spatially, as the wave goes out, there's places where we see these beats, but it's a flow in time as well. And so turns out if the sources have different frequencies, just a little bit, two sources with different frequencies, not the same, they're the same frequency, they'll interfere and produce standing waves. They'll produce beats when we consider the details of the superposition. The regularly spaced intensity changes occurring in time. All right, let's look to see how that comes about. So here are two sounds, one of frequency 1 and one of frequency 2, overlaid on each other. Now these are traveling waves, and when traveling waves interfere, we know they superimpose. If they're the same frequency, or therefore the same wavelength, they make standing waves. But what if they're a little bit different? Then the patterns are going to be more complex, and it's going to include regions where the sound level is higher and then diminishes down when you do the superposition. That's going to make the beats. And the beat itself is going to have its own wavelength, frequency, and period. But there, I just said too much now. Let's look at the picture that emerges to put some flesh on those words. So I am showing this along here. I'm going to algebraically add these two and put it on the combined waveform here. So I'm going to do it at several places, and you're going to have to trust me. I was trying to be pretty careful about this, but these dots represent various regions, you know, where the addition is done. So I did that in those locations. And when you do it completely over the whole thing, it produces a pattern that looks like this. There it is. Isn't that cool? All right, so that's how they superimpose on each other. And the wavelength of the beat itself turns out to be a lot different than the wavelength of the original waves, whether it's wavelength 1 or wavelength 2, which are slightly different but much shorter. Here, the wavelength of the beat, the intensity variation in the superposition of these waves, that's what it really is, has a spatial extent, and because it's produced in the medium at the same rate that these are, it's still the speed of the production of these beats is the same as the speed of the medium, and the medium is air. So notice that the wavelength here is pretty long in this case. All right, and you can see where it's a maximum and a minimum, and you have the maximum and minimum for each beat. And so even though the beats are not a tone per se, the intensity variation occurring fairly regularly gives kind of a wow, 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 wow type of effect, or a wow, 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 or brrr, bzzz. It can be, the beats can come very rapidly, or if the frequencies are really close to each other, it's a wow, wow, wow. And there, that's exactly what it sounds like. I just replicated it for you. But let's take a look at what that frequency of the beat is, the beat itself, which is just an intensity variation, kind of a warbling. And it's probably not going to surprise you too much that it's just the difference in the two frequencies. But by the time you've got destructive interference here completely, the next time you have completely destructive interference is when, is when the medium here, the two media, I don't mean to say that, the medium is not displaced here. It's not displaced here. It's not displaced here. Everywhere else along here, when you're adding these together, there's this continuous change, so to speak. I don't want to try and describe it anymore. It'll get confusing, and there's nuances to how this actually is, but it's just the algebraic addition of the two. So the end result is this being the beat frequency, where the unknown, if you haven't, it's like, what is an unknown frequency? You can get an unknown frequency if you know what one of the tones is, and if you know the beat frequency. And it's just the known plus or minus the beat. Because the unknown is going to be like the known, but different by the beat frequency. And it's either above or below. So let's do an example of that. So the example will be a tuning fork making a steady 400 hertz tone. You strike the fork, you hear a beat when it's next to a vibrating guitar string. And say 20 beats are counted in 5 seconds. So 20 intensity variations in 5 seconds with the tuning fork and the guitar string vibrating at the same time. So what possible frequencies are the guitar string? The beat frequency is 20 beats in 5 seconds, which is 4 beats per second. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, something like that. 4 variations every second. You can hear this. The frequency of the string then is 400, the tuning fork, plus or minus 4, which is either 396 hertz or 404 hertz. Which one isn't immediately obvious, but those are the possibilities. And that is how beat frequencies, along with a known frequency, can give you the unknown frequency.